around climate change, which is kind of why we're all here today. So with that said, I'd like to introduce the founder of the Arctic Ice Project and our CTO, Dr. Leslie Field. Leslie has degrees from MIT and UC Berkeley. She's an inventor with 58 issued US patents. She's worked at HB Labs and in Adjunct Labs. Hello, Leslie. And she's founded 2 technical MEMS consulting companies. She also serves as the adjunct lecturer at Stanford University, where she teaches a highly ranked annual fall quarter class on engineering, entrepreneurship, and climate change. So with that said, I'll hand it over to you, Leslie. Thank you.
Thank you so much, Tom, for that very kind introduction. And it's wonderful to have Tom Light aboard as our executive director. I have the pleasure of introducing Don Perovich, Dr. Don Perovich. And we have actually been in touch for about a decade. Don is one of the foremost experts in the world on measurements and trends in Arctic ice albedo, which means brightness, ice reflectivity. I met Don about a decade ago when he was working at CREL, which is the US Army's Cold Regions Research and Engineering Laboratory in near Dartmouth, New Hampshire, in Hanover. And I was impressed with his deep expertise in Arctic ice albedo. I described my work on ice preservation and restoration to him. This was our common ground. And he gave me a wonderful summary of his own work on the ice albedo feedback effect and a terrific tour of CREL's extensive testing facilities. We've stayed in touch ever since. I want to show you just 3 short slides, much of the information of which came from Don's own work, describing to you what we do, but more importantly for tonight, why our work, why we stay so very, very interested in what Don does. So I'm going to put this in a screen share mode as soon as I can. Yeah, it's always fun on a Zoom. Share screen. Get the right one. Start sharing. And so these are slides which you will see, a couple of these will be appearing in more detail in Don's presentation. I will say that what we live for here is we're working to give ourselves a bit of extra time, slowing what could have otherwise been an ever accelerating rate of temperature rise to let the world do what it needs to for getting to sustainable solutions, and every degree matters. Every degree is worth fighting for. Don will show you and narrate more beautifully than I've ever heard before in our dress rehearsal. A wonderful, impactful NASA video on what on earth, why do we care about ice loss? What is happening in the Arctic? How fast is it going? To us, the bottom line is that ice that was forming our heat shield in the Arctic, you can see it here in the upper left. Woo, I didn't mean to change my slide. In the upper left, how bright that used to be is pretty much gone now. We have had almost all of the bright reflective ice in the Arctic. Our historic heat shield has melted over the last just very few decades. And Don gets quoted. He is certainly one of the most expert people in the world on this. This was a year or 2 ago in NOAA's annual report card of what happens to sea ice. And you can read for yourselves that basically we've gone from having a substantial part of sea ice cover being bright reflective ice to almost nothing. What we do here at Arctic Ice Project, last slide about us, tonight is Don's night, but to show you why we're interested is so deeply in his work, is that as this ice disappears in the Arctic, we go from being able to reflect almost all of incoming sunlight in those 24-hour-a-day summer days up in the Arctic, going from being able to reflect almost all of it from large areas of the Arctic to being able to reflect almost none of it. Open ocean absorbs almost everything. Thin ice reflects a bit more. And what we do is we add a material, a thin layer of a safe material, which isn't showing up too well here, to make it instantly brighter. So that's our interest in this kind of work. This is thought-provoking, certainly, and we would love to talk with you more about that. But for now, I will stop sharing the screen and I will continue my introduction of Don because I haven't said all there is to say about him yet. He has published nearly 300 research works with nearly 30,000 citations and reads, including modeling sea ice, and he's a professor at Dartmouth College in New Hampshire. His research interests are sea ice geophysics, the interaction of sunlight with ice and snow, the Arctic system, and climate change. He has served as the chair of the Climate and Cryospheric Arctic Sea Ice Working Group, has received numerous prestigious awards from NASA, NSF, AGU, CREL, and more. Don was the co-chair of the Sea Ice Group of the MOSAiC expedition, which is going to be the focus of his talk tonight, which took years of planning and coordination with an international team to mount the largest Arctic expedition in history. Don, thank you so much. We are so honored to have you here with us tonight. Thank you.
The Arctic Ocean is a magical place. It's the frozen ocean at the top of the world. It's vast in aerial extent. You can see it in the map here. All of this is an area covered by sea ice. It covers millions of square miles, but it's only a thin veneer of ice, just a few feet thick. And always remember, this is a frozen ocean, so the ice is floating. That means the ice is moving, driven by winds and currents, and it can move several miles per day. And it's bright and it's white. It's our frozen ocean at the top of the world. And we'll see it's of great importance from a climate change perspective, because Arctic sea ice is both an indicator and an amplifier of climate change. How's it an indicator? Well, think of it this way. We have this area that covers millions of square miles, but it's only a few feet thick. It stands to reason that that would be very sensitive to changes in temperature. If it was getting cooler, we'd expect there to be more and more ice. If it was getting warmer, we would expect less and less. And indeed, we have the opportunity to look at this because for the past 4 decades, satellites have been tracking the extent of the ice cover and the age of the ice cover. And what we're going to look at now is an animation going through month by month, looking at the ice extent, how it moves. And we're also going to look at the age of the ice. You can see here this white area, that's older ice, ice that's 4 years and older. And the reason that's important is because old ice is thicker ice, and thicker ice is more resilient ice. So let's just take a look and see what's been happening. We start off going month by month. And the first thing you see are the seasonal changes, the heartbeat of the Arctic sea ice cover. It extends in the winter and retracts in the summer. This confirms our hypothesis that it is sensitive to temperature. Now, the challenge for us is to be able to sort between just the seasonal changes and any climate signal. So if we look at this, we can see that ice moves. It comes out here along the east coast of Greenland, and the ice that comes out here is gone. It goes into the north, to lower latitudes, and it melts because of heat in the ocean. Here now, as we go into the mid to late 90s, we see there's still a fair amount of this older, thicker ice. And in the summer, there's still ice pretty much filling up the Arctic basin. As we go into the 2000s, things really begin to change. You can also start to see this older ice starting to fragment into tendrils and filaments. And more of an ice loss here north of Alaska and north of Siberia. And we're coming up to 2007, which was an important year in sea ice because watch, there is this massive ice loss, a large retreat, and there's much less of this older ice from this time on. And the older ice is now getting all strung out. And as we go into 2012 towards another record minimum, we can see again another major retreat. And now there's just a very small amount of this older ice that's left. And because there's less of it, it becomes more fragile. And this continues on. We see the same sort of behavior and more of this older ice coming out north of Greenland and through July of 2019. So from this video, we should get a few things. First of all, there is this seasonal fluctuation. Second of all, as Leslie indicated, there's been a major loss of this older, thicker ice, and overall a loss of ice. And we can get a better idea of that just by taking a couple samples. What we're going to do is we're going to look at two cases, what the ice conditions were in September, because September is the best month to look at sea ice from a climate change perspective. It's the end of summer when the ice has reached its minimum extent, and any climate change signal would be the easiest to detect. So in 1984, we had around 2.8 million square miles of sea ice, and we can see how much of this old ice there was. And we can look at sea ice regionally and identify two regions: a graveyard off the east coast of Greenland, where the ice that's exported through here is going to be melting quite soon, but also a nursery off the north coast of Alaska, an area called the Beaufort Jar, because it's an area where ocean currents and winds have the ice go around in a circular pattern and can spend a few years here before going into the transpolar drift. And because it's going around, it gets thicker and thicker. Now let's jump ahead to 2012, which was the record minimum, and we see how things have changed. We've gone from 2.8 million square miles to 1.3 million square miles, less than half the ice that there used to be. And we can really see the dramatic decrease in the amount of this older ice. So we've gone from 2.8 million to 1.3 million. In millions of square miles, it's kind of a tough concept to really get your arms around. So to put it into some context, back in the early 80s, the September ice cover was around the same size as the continental United States. So we can just ask the simple question, how much of the United States melted? In the entire United States, east of the Mississippi melted. The band of states from Minnesota down to Louisiana melted. North Dakota, South Dakota, Nebraska, Kansas, and Oklahoma all melted. There's been a huge decrease in sea ice during this time. And it's important from a climate perspective to understand these changes. Warming in the Arctic is happening at a much faster rate than at lower latitudes. And in order to be able to understand and predict future climate states and climate models, we need to understand what's going on in the Arctic. And that was the motivation for MOSAiC, the multidisciplinary drifting observatory for the study of Arctic climate. It's a big experiment. Its centerpiece is the year-long drift of the German icebreaker Polar Stern that started in September 2019 to October of 2020. And MOSAiC was driven by an overarching guiding science question. What are the causes and consequences of an evolving and diminished Arctic sea ice cover? We wanted to be able to observe and understand this new Arctic Ocean, an Arctic Ocean that had less ice and younger ice. So let's take a look at MOSAiC by the numbers. MOSAiC is the biggest Arctic experiment that has ever been conducted. It's highly interdisciplinary and it's international. It was 10 years in the planning. It brought together contributions from 19 nations, used 5 ships. The cost is over 150 million euros. The science team was over 600 experts. The duration of the drift was 390 days. And of those days, 150 of them were days of night. The overall drift was approximately 2,500 nautical miles. It was big, interdisciplinary, and international. And I say it's interdisciplinary because as we identified the key problems we had to do, problems that would be able to address gaps in these climate models, we realized that we needed 5 teams. Team from the atmosphere, sea ice, the ocean, biogeochemistry, and ecosystems. And all these teams were brought together to work on the same basic questions, and we were kind of under a general fabric of modeling. We had this integrated experiment with 5 elements. And as I said, the centerpiece was the drift of the polar stern. This is a map that shows the drift. The dotted lines are when the ship was under power. The solid lines were when it was drifting. During the planning stage of MOSAiC, we had a whole Arctic to decide where to work, and we decided we wanted something that went from the Eastern Arctic through the Central Arctic and then out the Fram Strait east of Greenland. This was an area that was important that we didn't have much information about. There hadn't been as many long-term field experiments conducted there. And you see the drift is shown here. It's color-coded. There are 5 legs to the experiment. Nobody was up for staying the whole year. We're able to rotate teams and resupply the ship by other ships coming up to assist. And then we actually came out of the ice in July of 2020, and then had to go back up to do the last few months again. So this was the drift of the ship. Now, if you're working in the Arctic anytime, you realize that there are significant challenges to working on the ice. The difference for a year-long experiment, you get to experience all of them. You get to experience the high winds, the blowing snow, the months of total darkness. You get to experience the moving, breaking ice. Remember, this is a floating ice cover that's only a few feet thick, and it can break apart, forming areas as shown here called leads. And what breaks apart can come together, forming mountains of ice called pressure ridges. It's real-time plate tectonics. These events happen in just a few minutes. And you don't really know where they're going to happen, other than it seems like it's always the most inconvenient place. Now, the challenges of winter are severe with the darkness and the cold, but that doesn't mean that summer is easy. And it doesn't mean you don't have to worry about friendly visits from polar bears. We had quite a few bears visiting. We realized it was their home field. We respected them, and there weren't any negative interactions. They did sometimes have too great an interest in our equipment. The challenges continued into the spring and summer. Here we see a scene from late spring where there was a breakup event. And the problem in late spring, since it's warming, these leads don't freeze. And you have to learn to live with them unless the ice deforms and they crunch back together again. But it's not just winter. And when melting starts, it has its own challenges. It complicates mobility. There's a period of a few weeks where the snow is melting and getting around is like wading through waist-deep slush. And then there are these surface features called melt ponds, where the melt water from the snow and the ice collects on the surface, forming these very beautiful blue ponds, which can be a little bit difficult to walk through. And if you're bringing equipment, you may have to build a bridge across them. Now, the ponds were one of the areas of great scientific interest, and we wanted to measure the properties of the ponds, how deep they were, how wide they were, and having the water there can make the measurements difficult. Now, you may look at this and say, well, that doesn't look that hard. Looks like it would be kind of fun. And it was. But the ponds have different depths, and sometimes it can make it very difficult to do those profiles. So we had darkness, high winds, polar bears, melt ponds, leads opening up. To be honest, we expected all those things. We planned for all those things. We were ready when the events happened, and it wasn't that big a deal. We had pretty much planned for almost everything. What we hadn't planned for was a global pandemic. As we were getting ready to do the rotation between Leg 3 and Leg 4 at the end of March, countries started closing. We had to cancel that rotation. We had to cancel some aircraft missions because the planes couldn't land in countries that were closed. International icebreakers that we were counting on to do some of the rotations suddenly were unavailable to the quarantines of their home countries. Well, there was a period of a lot of questioning, a lot of planning. Could we continue this? And we decided that safety was paramount. But if we could do it safely, we wanted to continue the experiment. We were able to find German research vessels to help with the rotations. And the Leg 4 team went into quarantine. They all went to Bremerhaven, were tested upon arrival, went into their hotel room where they were locked down just inside the hotel room for a week, were tested again, everyone passed. Then they got to get out of the room, but still were locked down inside the hotel. They were tested a third time, everybody passed. They were loaded on a bus, directly taken to the ship that would take them out for the rotation. Team 5 did the same thing. We were able to continue the experiment to the end, and the MOSAiC bubble worked. We had no cases. And this is really a testament, first of all, to the hard work done by the logistics team and the medical staff of the Alfred Wegener Institute, but it was also a testament to the dedication of the science team and the crew that was willing to go through these extra quarantines just for the opportunity to keep the experiment going. Now, we have lots of results. We have terabytes of results. In an interest of time, I can only give you a sampling of that. And what I want to concentrate on are some results from sea ice, because sea ice is what I do. Our approach to sea ice, we wanted to look at changes in the ice properties over space and time. We wanted to look at the snow, how deep it was, what were its properties, how thick was the ice, how did the ice grow in the winter and melt in the summer. We wanted to follow photons and look at the partitioning of sunlight to what was reflected from the surface, what was absorbed in the ice, and what was transmitted into the ocean. And we also wanted to look at ice dynamics, how it moved around, what were the internal stresses of the ice, and how did the ice deform? How are these leads made? How are these pressure ridges made? We wanted to look at changes over space and time. And the advantage of an experiment like this is that you can learn a lot just by being there and looking around. You can watch the ice evolve. You can watch these changes over time. Here's a picture. You can see the ship, the ice station. On the 6th of June, there's just the first inklings of melt. You can see some little melt pond features here, but in general, the surface was just beginning to melt. You come back 3 weeks later and melt is in full swing. There are large melt ponds everywhere. You can see some areas where there's actually sediment-laden ice. And then we come back a little over a month later and it's all come apart. What happened is the drift of the ship took it down to the edge of the ice where wave action just took our big flows and shattered them into a lot of smaller flows. So we can learn a lot just by watching the ice evolve. We can also learn by seeing how the ship drifted. Now, I talked a lot about how MOSAiC is the biggest experiment ever. It wasn't the first, and it really wasn't the most audacious. That goes to Fridtjof Nansen and the Fram. Nansen was a famous Norwegian polar explorer that back in 1893 wanted to go to the North Pole. And his plan was to freeze a ship into the ice and drift to see how close he could get to the North Pole. And we decided that we were going to go into the drift track of Nansen. And you can see the similarities in this plot here. Here's Nansen cruise, drifted along, and then came out of the ice here. Started on the 22nd of September, ended on the 28th of July. Here's the drift of the polar stern, starting on the 4th of October, coming out the 30th of July. So you can see there's some similarities. There's the same general pattern to the drift. There's a similar start time, a similar finish time, but there are two big differences. The first difference, you can see we started much further north. And the reason we started further north was there's no longer September ice where Nansen started. There's been that much of a retreat in the ice over recent times. The second difference is, well, we started at around the same time and ended around the same time, The MOSAiC drift was 10 months. The drift of the Fram was 10 months and 2 years. We were much, much faster. And one of the things we're working on now is trying to separate what were the causes of that speeding up that we experienced, how much of it was due to changes in atmospheric circulation, and how much of it is due to the ice. Thinner ice is easier to move. We moved a lot faster. Now, we did more than look out the window and see where our position was. We made lots of measurements. And I would just want to take a look at one set of our measurements that are oriented at the ice albedo feedback. So what's the albedo? Well, the albedo is my favorite geophysical parameter, and it's my favorite for 2 reasons. First, it's simple. You get the right instrument, you point it at the sky, take a measurement, you flip it over, point it at the surface, take a measurement, and divide. Trust me, in geophysics, it doesn't get any easier than that. But it's easier still because if all the light is absorbed by the surface, the albedo is 0. If it's all reflected, the albedo is 1. Take 2 measurements, divide, and you know ahead of time it's bound between 0 and 1. Now, the ice cover covers most of that range. The albedo for open ocean is around 0.07. For snow-covered ice, it's around 0.85. That's the albedo. What's the ice albedo feedback? Well, the ice albedo feedback, the surface absorbs some sunlight. That absorption leads to melting. That melting lowers the albedo. That lower albedo means more sunlight absorbed, which means there's more melting, and a lower albedo, and you get the idea, and on and on and on. It's a feedback mechanism. And if you have a climate model, you have to get these feedback mechanisms correct, because they're a way that the general nudge to the system can be amplified into a big shove. The ice albedo feedback shows how sea ice can be an amplifier of climate change. Because of the importance of albedo, we made lots of albedo measurements. There were several albedo lines that were 200 meters long, where we would go along measuring albedo every 5 meters and doing those repeat measurements every few days. This was done looking at across the entire solar spectrum and also at individual wavelengths. And we had sites looking at particular ice types to see how they evolved. And here you see results just from one of these surveys taken on July 27th. And I picked out 3 points. The lowest value was around 0.2. And that was for this melt pond here that was kind of dark and scary looking. The highest value was 0.7. This was for bare ice that had a surface layer a couple inches thick of just granular melting ice crystals. And then there was this intermediate albedo of around 0.4. That turned out to be this bright blue pond. So making these albedo measurements, we were able to look at changes in the albedo over space. We were also interested in changes of albedo over time. And what you see here is a time series of albedos, starting in May, going up through October. And what it is, each point represents the average albedo along that 200-meter line. We wanted to get something that was a representative sample of the ice conditions at that time. And you can see we start off when the surface is covered by snow, the albedos are large, around 0.8. And then as we go into summer and melting starts and these melt ponds form, there's a decrease in albedo until finally there's fall freeze up. The ponds freeze over, it begins to snow, and the albedo goes back up. And as I said, we have lots of data like this. This is just to give an idea of some of the changes we saw over space and over time. Now, one of the things that we've talked about in MOSAiC from the very beginning, that the data are the legacy. The MOSAiC data set is something that we're going to be leaving for future generations of researchers. And because of our agreement of the importance of data, everyone involved in MOSAiC had to sign the MOSAiC data agreement. The idea is to promote fairness in data, accessibility data, with a goal of a complete data set that's archived and published with full metadata explaining everything we did. There's this very strong commitment to data sharing and archiving. Now, some of my friends say, well, hey, now that MOSAiC's over, what are you going to do with yourself? Well, the field experiment is over, but the excitement continues and the fun is just beginning. It's time now to analyze this data set, to integrate different data sets, to synthesize the results, and to integrate those results into models. Here you see some of the team pictures. This is a team picture of the Leg 4 sea ice team. And one thing to point out about it, one thing that was really important in MOSAiC, there was a strong component of early career scientists. And what could be better than to be starting your career out as part of the largest ice experiment ever done? Now, I'm looking forward to spending the next few years working on MOSAiC data, trying to understand the changes we're doing, trying to unravel the mystery of this new sea ice cover. But I want to emphasize that it's not just an intellectual exercise. There are consequences to this changing sea ice cover today. There's an impact on coastal communities. There's changes in tourism. There's also major changes in shipping and political issues such as the law of the sea, economic issues. There's a lot of natural resources under the Arctic Ocean. People didn't worry about them when it was covered with ice. There's also potential impacts on ecosystems that we're just beginning to try to understand. And then there's a lot of research being done now looking at connections between the loss of sea ice and mid-latitude weather. And the key is the Arctic is part of a system, part of a global system. And what happens in the Arctic doesn't stay in the Arctic. It has consequences today. Thank you very much.
Thank you, Don, so very much for doing this. What an inspiring lecture this is. I believe our next thing we get to is Q&A with questions from the audience, questions from ourselves. And gosh, that's just one of the most inspiring expeditions I have ever heard about. Oh, and people are just writing. If you have the time to look at the chat, Don, you will see people writing so many thanks to you. How important is the Arctic to the Earth's ecosystems and humanity's future? You said a little about it. You want to expand on that at all?
Yeah, I think it's one of the things, I've been a sea ice researcher, and one of the things probably in the past 15 years is first realizing that sea ice is just part of the Arctic system. And now taking that a step further and understanding that the Arctic is part of a global system. In a simple sense, I mean, you could say, well, it's far away. It's really interesting to hear about it, but how does it really impact me? As you mentioned in your remarks, sea ice is a great reflector. It cools the Earth. It reflects 85% of the sunlight when there's snow on it, and that helps cool the Earth overall. And as we lose that sea ice, we'll be absorbing more and more heat, which will accelerate warming.
Fantastic answer. We've gotten some questions coming in right away while you were answering that. I think this is prompted by your describing accurately the kinds of difficulties you have making measurements like this right there on the spot. Can satellites make many of these measurements?
Yeah, I mean, satellites are an incredible tool to get the large scale picture. That right now, we have 42 years worth of information on the ice extent, how much area is covered by ice, and what fraction of that area is ice compared to open water. And that's just, I mean, that's one of the canonical warming data sets. There's also satellites that can look at in the past decade, there have been satellites that can measure ice thickness. There are two satellites. One is a European Union satellite, Cryosat, that uses a radar. Uh, the NASA has a satellite, ISAT-2, that uses a laser. And both of these basically measure how high the ice is floating, and then from that determine how thick it is. So that's a great advantage. There's also work looking to try to get an idea of how deep the snow is. So the satellites provide an invaluable resource. There's also autonomous instrumentation. Um, One of the projects I'm working with, we put in these autonomous buoys that can measure ice temperature, ice growth, melting on the surface, melting on the bottom. And we co-locate those with buoys looking at the ocean and looking at the atmosphere, because these big experiments don't come along very often. And I think what the experiments can give you that the autonomous instruments can't, and the satellites can't, is that very detailed look at the system, what's going on a small scale. And I didn't touch on it, but one of the things we're starting to unravel is how does the changing ice impact primary productivity in the ocean?
Mhm.
And those kind of measurements, well, you can't do it from the satellite, and it would be hard to do from a buoy. So I think they all play a major role. And by synthesizing all the data together, maybe we can figure out what's going on.
Beautiful answer. There are other questions coming in. I'll try to synthesize so that we don't go till midnight because you've got a lot of people interested. One is on ice thickness testing. My understanding is that getting to do some ice thickness monitoring locally from the ground is a very helpful augmentation to the satellite imagery, for instance, because of cloud cover and such. Or have things advanced that much in the satellite imagery?
They've advanced a lot. Again, the satellites have a footprint of a certain size. And sometimes there are features like these pressure ridges that may be smaller than that footprint. They're one of the things that the ICE team was heavily involved with was surface surveys of snow depth and ice thickness. And there's a nice electromagnetic induction instrument that you drag along in a sled, and you could get profiles of ice thickness, which sure beats the old way of drilling holes in the ice, which is a lot of work and kind of a big mess.
Mhm. Yeah, I've experienced some of this on our small
Yeah.
scale. Let's see. Going back to the importance, the changes, what are the most important signs of hope? And how can we as individuals work towards helping in this? You know, you're pointing out just what big changes we have and that it's going to matter to us and to ecosystems. What are your signs for hope?
Well, I have to confess, I'm inherently an optimist. So I look at things in a positive sense. And I think there's, a growing, I mean, I look back when I've been doing sea ice for a while, and it's only really been the past, say, 25 years where it's taken on a climate change perspective. And when we were first doing this for an earlier experiment called Shiba, which was a year-long drift experiment in 1997 and 98, there was still a question whether or not there was any warming. And if there was warming, was it connected to human activity? Well, that question's been answered. And you see, people around the world realizing this is a problem, realizing we have to do something about it, international agreements being made, cabinet level people assigned to climate. I think those are reasons, for hope. And I think it's the sort of thing we can all make a contribution uh, to reduce the amount of CO2 we put in the atmosphere, working on ways to determine how to respond to these changes. So I think there's plenty of reason for hope coming from somebody who's an optimist.
I do love that we're getting much more international and very high level national attention all over the world on how important this is. One person asked, is protecting the polar ice cap specifically mentioned in the Paris Climate Accord?
I don't know. Um, I
I don't
know
either.
that,
I think maybe not, but
yeah, you, you've given me a good homework assignment. I have to say, in general, I think there's a real appreciation for the importance of the Arctic. And if we look at the Arctic system, I mean, you can ask yourself the question, what makes the Arctic the Arctic? And I would say it's the perennial presence of ice. Ice in the ocean is sea ice. Ice in the land is permafrost. Ice on the land is glaciers and ice sheets. And that's what makes the Arctic the Arctic. And if we start to lose that ice, it becomes something, different.
so there's a question that ties right into this. What's the key driver of ice melting at the end of the Arctic season? Is it air temperature, wind speed, water temperature, water currents, solar irradiance, cloud cover loss, ... question. I like the way they left that
I
open-ended.
mean, that's a great question. And then when I was showing that animation, I mentioned how 2007 was at the time a record minimum September ice extent. And it's still the largest year-to-year drop that we've ever seen. And that really, I still remember going to the meeting of the American Geophysical Union that year. And that was all the Arctic group could talk about, was this ice loss. And there were lots of talks, with audiences draped out into the hallways, which is really pretty unusual from my prior experience. And the question was, what was driving it? And the answer was pretty much all the things that were mentioned in the question. Uh, and I think it goes back to these feedbacks. And for the buoys that I talked about, one of the things that we've seen is that you don't want to mess with the ocean. When we look at some of the changes in the areas where we've seen major ice loss, like north of Alaska, we have seen increases in the amount of melting on the surface, where the surface is what's responsive to air temperature and incoming sunlight. Where we've seen huge increases is melting on the bottom of the ice, heat in the ocean, because the ocean can melt ice really quickly. And we believe that that's a consequence of there being more open ocean that's absorbing more sunlight and getting that ice albedo feedback.
Yes. There's a question right into this. Have sea currents changed significantly in the Arctic over the last couple of decades?
I don't think so. There's a big project on the Beaufort Jar, the area I mentioned, and it's run out of Woods Hole, and they do some serious oceanography there. We have some of our sea ice mass balance buoys as part of that. And I think they've seen changes in the amount of fresh water that's entrained. And beyond that, I'm not sure of the answer. But if they Google Beaufort Jar exploration project, they'll be able to find out all about it.
Yeah, that's awfully important. As you mentioned, that's the historic nursery of multi-year sea ice.
Yeah, and there's another group studying that right now, if we look at the ocean and saying the ocean is important, it's very important. The Arctic Ocean has a surface layer that's kind of disconnected from what's underneath it, because there's warm water down below, but there's this colder, fresher water on the surface that kind of isolates the sea ice from what's below. And there's a lot of interest over in the Eastern Arctic if that warmer water is getting closer to the surface, which could melt a lot of ice in a hurry.
Yeah. I'm going to ask a couple more of these technical questions the audience has, and then I believe we go to a bit of some more comments from our executive director, and then to a sort of follow-on question and answer. So I'll do another couple technical ones. Some of the follow-on question and answers, I think we'll do things like, what are your polar bear and hair-raising stories that you've had? So don't go away if you don't.
Okay, I'll be here.
Yeah, you certainly will, but our audience, I hope, will listen to those too. What was the most obvious sign that climate change was having lasting effect on the future of the Arctic? How are the local people needing to adapt to the changes in their environments? And are they making progress in their efforts? This came from John, who asked.
Yeah, I think there are challenges. There's the one slide I showed of the house falling into the ocean. I think that the people that live in these coastal communities or anywhere in Arctic communities are very resilient. But there are challenges. For example, if we look at sea ice provides services. During the winter in the coastal community, sea ice is a highway. You can drive and visit your friends in a
Yes.
nearby community. You can go on the sea ice to go hunting. And without that ice there, that changes things. And it also becomes less safe. That living in an area for thousands of years, you develop a certain seasonal tempo. And when that starts to unravel, it makes things a lot more difficult.
Yeah, yeah, I agree. Hunting is terribly dangerous. All of it is. A lot of land being lost. Um, let's see. There's a question about our work. So I'll take a quick digression into that from Laura N. Saying, I'm very curious as to what you think of the ICE 911, we're now Arctic Ice Project, approach to find and deploy a material way on top of an area to preserve ice, and whether this is a feasible approach. If so, what would need to happen funding-wise, stakeholder-wise, to begin to address the vastness of the large physical area? And if not, what other options might there be to stave off Arctic ice melt? So I think I'll take a first iteration of that. And then Don, if you have comments about that, we'd love to hear them. Part of what we're doing within our organization is collaborating with ecotoxicological and marine biologist experts to make sure that what we're doing is a safe approach. What we are working with are the safest, most practical, most affordable, effective materials that we have found to date, but there's still work to do to make sure that that's true. And we're working with various other stakeholders, including people who live in the Arctic, international bodies, trying to see what the ground rules need to be, the frameworks for policy and such, trying to help develop those, and working with climate modelers to see, are there some very finite areas within the Arctic that work to have a leveraged effect that helps a lot. And so I think our climate modeling partners actually are in the audience, Climaformatics. There's other bigger national labs who are beginning to want to partner with us to help answer some of these questions. So there's a lot of work trying to make sure that this is a safe and sane approach and make sure there are ground rules. But Don, you've seen a lot of these approaches, I'm sure, as well. What do you think?
Well, I really enjoyed listening to your answer. And one of the things that we've talked about this before that I'm really looking forward to is to read the modeling paper you did, because like I said, the ice cover is the size of the United States. So it's hard to scale anything up that big. But if you can denote key areas where an application of something could make a big difference, where you get that leverage, I think that would be an important thing to know. And I look forward to reading the paper.
Great. Yeah, our modeling partners are working furiously to ready that for publication, and
Yeah.
it's exciting work. Yeah, thank you for that. I think at this point we turn it over to Tom for a bit, and then we come back with more of these wonderful questions people have been asking. Thank you, Don.
Great. Thanks, Leslie. Thanks, Don. Like Leslie mentioned, please stick around for the breakout session, which will start in a few minutes. However, before we move to the session, I just wanted to take a brief moment to, sounds kind of echolalic, but to thank Don for his presentation today, for our esteemed panelists. I know that you have a busy schedule, Don, and we appreciate the time that you allotted us. And we also wanted to thank the audience for dialing in today. I hope that we delivered an invigorating kind of presentation on why the Arctic matters and a positive call to climate action. I'd also, while simultaneously thanking everyone on today's call, just remind everyone that the Arctic Ice Project does rely exclusively on private donations to do our work. And like many nonprofit organizations, we're facing higher than expected operating costs due to the global pandemic. So, would urge you to consider the Arctic Ice Project as part of your philanthropic legacy. And in that regard, I know that our Robert has shared a web link for donations, and of course, there's the website at arcticiceproject.org, which you could visit to make a donation as well. And, truly sincerely speaking for Leslie and the entire team, for those of you that just would like to learn more about our work, just reach out to us. Would always, like to have those private conversations with our network, and no donation is required for that. So I wanted to thank everyone involved, and then I guess I'll hand it, I think we'll move over to the breakout session now at this point, Leslie. So I'll hand it right back to you.
Okay, thank you so much. Thank you so much, Tom. And thank you, wonderful audience, for all of these wonderful questions. I will point out that some of these questions have been answered by some of our team. Rob Moss and Alexander Schultz, our principal engineer, have both been answering some of these you'll see in the Q&A. And I also appreciate all of these wonderful thank yous that are appearing in the chat too. These are just encouraging to see. It takes a lot to do this kind of work, so we're filled with appreciation for you. Dawn, I think we're going to get you back to some more of these terrific questions. So if you can be visible again, that would be, yeah, thank you. That's great. What got you interested? What caught you about Arctic ice? These are the more human interest questions at this point, I think, partly.
Well, I was a physics major as an undergrad, and I really enjoyed physics, but I wanted to do something outside. So I went off to the University of Washington to study geophysics. And at the end of the first year, you take a qualifying exam, you pass, and then you have to settle down and find a topic area. And what was great about the University of Washington, there was incredible choices. You could study volcanoes, you could study earthquakes, you could study the magnetosphere, or you could study glaciology. And I was making the rounds talking to different professors. I talked to one who was doing sea ice research, and he started telling me about walking on frozen oceans under midnight sun and the beauty of the Arctic and the majestic polar bear. And he was laying it on pretty thick. And when it was time to leave, he went to the bookshelf, pulled out a book and handed it to me and said, "Read this and then come talk to me." So I left thinking, geez, that was a strange experience. And I got home and sat down to take a look at this book. And 4 hours later, I finished it. It was Endurance, the story of the Shackleton expedition. And I went back the next day and signed up, and was really excited about this chance to go out into the field and walk on this frozen ocean. And then I spent the next 3 years doing laboratory experiments before I actually got a chance to go out on this frozen ocean. And I also learned that my advisor had never actually been on ice himself because he was more of a modeler. But in the end, it all worked out great.
That's pretty funny, but I really enjoy that. Let's see, there was polar bear interactions I think you have experienced in your adventures. Can you say more about your interactions with them?
Yeah, I've I still remember the first bear I ever saw, and it was in the marginal ice zone east of Greenland. And when I got back on the ship that evening, I wrote 2 pages of the most flowery prose about nature's marvel.
Mm.
By the end of the week, they had just become a total pain because whenever they came by, you had to go on back on the ship until they left. But they are incredible. And they're the old Arctic joke is that polar bears are driven by 2 things, curiosity and hunger. And they're curious as to whether or not they can eat something. So they're really pretty interesting. I've only been stalked by a bear once.
I have been very, my attention was grabbed when they told us in our orientation up in the Arctic, up in Utqiagvik, where we do some field work, that the polar bears actually will actively hunt us.
Yeah, on one experiment, there were 2 of us out working, and I was done with my stuff, and he had a couple more measurements to make. And then this bear showed up, a couple 100 yards away, and he really wanted to finish the measurements. So I said, "Okay, you finish the measurements, and I'll keep an eye on the bear," because we are only a few 100 yards from the ship. And so I'm have my telephoto lens on to try to get some pictures. And the bear is just laying there on the snow. And every so often it would lift its head up and smell the air. And I'm thinking, isn't that cute? And then I noticed each time it lifted its head up, it inched forward a little bit. And I realized that, yeah, we were upwind of this bear that was slowly closing on us. And the morning's measurements were now concluded, and we
Yeah,
just headed back to the ship.
I think that was a wise choice. That falls into what were some of the biggest challenges about the global pandemic? Did anybody on the expedition actually suffer from COVID? Is everybody okay?
No, and there was, I mean, the MOSAiC Project Board had long discussions about, what to do, because there was a period, the second half of March, where we were meeting like every other day. And in the alternate days, the people in Germany at the Alfred Wegener Institute were working on things and would have a plan, and 2 days later would have completely unraveled. But from the very beginning, the idea was we want to do this, but if we can't do it safely, we'll just pull the plug on the whole thing. And so there is a tremendous effort, and really we preceded the NBA bubble. But instead of having in Orlando, we had on an icebreaker in the middle of the Arctic Ocean, because the realization was you had to make sure that nobody that got there had COVID, because in that situation, if one person has it, everybody has it. I mean, I've been in ships or field camps where somebody will come in and they'll have a cold, and 3 days later, everybody has a cold. So, it was a perfect bubble, and, it worked out pretty well.
Uh, Rob, what is one of the top questions that you would like me to relay here? I'll let you think about that while I ask a couple that have been asked that Alex has been busily answering some and Rob has been busily answering some. Um, how accurate is satellite data? Are there reliable satellite data sets for sea ice albedo? I think this goes to some of the other comments that people have been writing in here of you need a certain amount of ground truthing no matter what. What are the pluses and minuses? How much do you really trust any one measurement? Do you need a whole suite all the time?
Yeah, I mean, I'm a real fan of satellite measurements, even though that's not directly what I do, because it's the way to get that big picture. If you look at the longest record, we talked about its ice concentration and ice extent, how much area is covered by ice. And even that, there's some, I think there's like 10 different ways to process the data. And one thing that's important to remember, the satellites aren't measuring ice extent or ice thickness. They're measuring an electromagnetic signal that has to be translated into a geophysical parameter. And there are several different translation schemes that for ice extent, for example, there's several different ways to do it, but they all agree on the fundamentals. There are some different nuances and things, but basically they all agree on the important things. You mentioned albedo. Albedo's challenging. I mean, there are measurements of albedo from space that we can use. There's a couple problems. You can't measure albedo per se from space, because the albedo is something where you're adding up all the light that comes in over a whole hemisphere. And the satellites are just looking at a narrow field of view. So you need, again, a translator to translate that measurement of a property called radiance, which is like looking at a narrow beam, to the albedo, which is usually a property called irradiance, which is averaging over a dome. That's one problem. The bigger problem is it's cloudy most of the summer. And the satellite can't see the surface, so you can't measure the albedo. So if you look at the albedo records there are, they're pretty good, but they're pretty spotty.
Thank you. Yeah, and there is much more on this in the chats, both the chat and the Q&A chat as well. But thank you. You've got that firsthand experience that you just, it just shows. There's some questions of, well, I think maybe one of the more touching ones is there's somebody who was tuning in from Phoebe from the UK saying it's 1:20 a.m. but loving this so much and totally worth it. So that's pretty dedicated.
Yeah. Yeah. Thanks for tuning in.
Yeah, that's amazing. And there's somebody else saying, he asked a couple of really good technical questions too. John, I look for more information all the time. Thanks for your presentation. How can I, as an ordinary citizen, help or lead in helping to save our environment?
Wow. I mean, thanks for wanting to do it. I mean, that's a great question that I ask myself a lot. How can I do it as a regular citizen? And I think it's things like be active, vote, uh, look
Yeah,
for organizations that maybe you can be part of, you can volunteer for, um, and support initiatives to reduce well, reduce greenhouse gases.
I will say there are some excellent books, and you might, oh no, tell me that I can't do it. There's a huge book that I'm holding here, but I can't do it with a virtual Arctic background there, saying it's called Into the Arctic Ice. You've probably seen this, Don. It's a hardcover, huge book called The Largest Polar Expedition of All Time by Esther Horvath. So you can read more about this.
That must be brand new
Yeah, it is.
because I haven't seen it yet.
Oh my goodness.
I mean,
Okay.
I know I mean, another thing about MOSAiC is they work really hard on outreach. That book's an example. For each of the 5 legs, there were 2 dedicated media people. Uh,
Wow.
there's also going to be a planetarium show based on MOSAiC. There are, all sorts of articles written about it. And I heard there's going to be I think either it's done or it's being worked on a documentary about it. So there's really been a lot of outreach activity.
That's wonderful. I think I'm trying to wrap this up within a couple of more minutes, unless somebody tells me that we should be able to take more time, in which case, please, Tom or Rob or Alex or Carol, break in and say that we should let it go much longer. But there's a couple of questions about um, what is our status? What's our research status? Some of the people dialing in have been looking at our work for quite a while. And I will say the most exciting thing to me is that we've been building the team out and developing a really solid 5-year plan, which includes a lot of collaborations with true experts. I mean, people like Don Perovich, scientists who really know what's going on, are absolutely vital to what we do. Because if we don't know that reality, there's no way we can address it effectively. There are international groups reaching out to collaborate with us, and we've got a number of proposals, 3 of them that are getting submitted shortly for these collaborations with places like NCAR, so one of the big climate modeling laboratories in Boulder, including our current climate modeling team from Climeformatics, who are terrific. There are 2 Norwegian groups who want to help us, work with us on marine biology and safety questions, and also on some deployment and areas. And is grease ice very, very important? So many questions like that we're getting to refine. There's a clinic we're working with Harvey Mudd College on some of our deployment questions. And we're seeking more and more collaborations with indigenous people, the people who actually live in the Arctic. If we fail to do co-development with them, if we don't reach out, we're not doing our job right, and we're not benefiting from all that incredible depth of knowledge. So people have asked a little bit about that. We work with Native Corporation when we're working up in Barrow, which is now gone back to its original name of Utqiagvik, which is as far north as you can go in the US. So there's a lot of that. I would say that we've gotten through all the proof of concept testing in many of our technical areas that we need to have, despite COVID, despite funding challenges from the pandemic. But there's a long way to go. We're aiming to have things within 5 years or hopefully less, getting more and more ready to be able to partner with the international community to make these decisions about what's in the best interest of humanity. We shouldn't make those decisions. We can help give all the information needed to make those decisions and then to help them implement. So those are some of the where we are. It's a big enterprise, and we're not going to do it alone. We need people to help us with. Um, I think that's sort of a good summary on that. Dawn, should we end up with temperatures, scary stories, or inspiration? Before then, we let everybody but the hardcore leave, and then if you're willing, I'm sure happy to stay on as long as anybody else is. But Dawn, what are some really great tales you'd like to end with?
Well, I mean, it's just lots of fun to work in the Arctic. I mean, it's hard work. It's either you're cold or you're wet. I mean, when you're working in the winter, there's three things you want. You want your face to stay warm, you want to be able to breathe, and you want to be able to see through your goggles. And you can pick any two of those, but you can't have all three. So there are things like that. After all these years, I'm still on the quest for a pair of gloves that'll keep my hands warm, though hand warmers really help. There's lots of stories about working in the cold. One that comes to mind, it was part of this Sheba experiment, and it was November 1997. We were deploying a bunch of sites. There were four of us from Crowell that were working together, and we were drilling a bunch of holes and installing some instruments a couple miles away from the ship. And we started that morning. It was lunchtime, and we had like another hour or two to work. And we didn't want to go, I don't want to say, let's go back to the ship because it takes time to get there. It takes time to get back. So I decided it would be great if we just worked through lunch to get this done and then go back to the ship. Well, it was like 35 below, and around 1:30, each of us got very hungry and just kind of crashed and went to our inner self, and it wasn't pretty at all.
I know
And
what you mean. Yeah.
and the consensus of the group was, Don, you can do whatever you want. We're going back and get something to eat. So you do have to keep the engine fueled at all times. And a thing that I learned from an old Arctic hand the first time I was in the Arctic, that the first rule of the Arctic is eat as much as you can whenever you can. It's just so much fun to work on that. I've done, well, back in the day, I did some under ice diving, and it's just, incredibly beautiful under the ice.
That's that's nice. You know, in your theme of crashing, I've been told that we should have maybe two more questions, and I'm realizing it's a lot of people's dinner time. So I think what would we wrap with? Rob, what are the top two questions that we should get answered? You've been getting to follow the chat more.
There are a lot of them.
But oh, here's one
I
that
know.
grabs
Yeah.
my attention. And you get to do the final one, Rob, of which one. I like this one. Gary Latshaw asked, would interventions to preserve ice along the coast be effective to constraining methane emissions from seafloor permafrost? We haven't talked about methane much at all, Don. What would you like to say about that general area?
Yeah, I mean, I don't know a lot about methane other than there's a lot of it in the tundra, and there's some at the seafloor, and that methane is an incredibly powerful greenhouse gas, and that's another feedback that people are really concerned about. I think if you have an ice lid on top of the ocean, that's going to help keep it cool. And one of the things that's interesting about the Arctic Ocean is if you look at the bathymetry, it's really pretty shallow and off the coast. where a lot of these deposits are. So it, you know, possibly could help out, but I'm not a methane expert by any stretch of the mind.
Okay. Actually, I have a favorite, one more that I could knock off quickly, Rob, and then yours. Somebody had the idea, besides dragging white sheets across the melting ice, what other things are being enacted by our organization or peers? We are not doing white sheets. I started with white sheets. It's a good place to start, but they are impractical and difficult. So what we're using is something that's more like a floating hollow white sand, very foot friendly, very round. And that seems to be much more practical. But Rob, Rob has done much of the organization of this and much of the communication with you all. What's your favorite last question?
My favorite last question is, are there any citizen science projects connected with these efforts? Is there any way we can help?
I know for the work that I do, we have an outreach program with our local middle school for their science classes, where they have a station similar to our autonomous buoys. And then we go in there and talk about climate change in the Arctic, and they make the same set of measurements and develop hypotheses. And then test those hypotheses. And there's some interesting findings. You know, I live in Hanover, New Hampshire, and one of the things that I toss out, will it ever be colder in Hanover than it is in the high Arctic? And usually the students think, you know, no way. And almost always there's a day or two where it's colder here than up there. And the other one is, who's going to get more snow? You know, Hanover or the Arctic, and Hanover always wins. Now, the Arctic keeps its snow a lot longer, but on sea ice, the average snow depth is maybe a foot, so it doesn't get a lot of snow. One thing, since that's the last question, I'd really like to thank everybody that tuned in, particularly those that are delaying their dinner. I mean, talk about dedication. Yeah, I really appreciate your interest in the Arctic and sea ice and in MOSAiC. So thanks so much for tuning in.
Don, thank you. What a total honor this has been. Thank you. And thank you, audience, everybody who was interested, had these excellent questions. Thank you so much. You know where to reach us, I think. Thanks a lot, Don. This is
You're welcome.
phenomenal.
You know, could I also just add that if they could follow us on social media, it does make a big difference. Instagram, Facebook, any of our accounts, that would be very helpful.
Very true. Very true.
Thank you, Carol.
Thank you so much, everybody.
Yeah, thanks everybody for joining. This is fantastic. Don, special thanks to you. Really appreciate the time you spent with us.
Yeah, this is getting late for you, and thank you. Wonderful.
Yeah. Thanks, everyone.